Good afternoon, good morning, good evening, and good night uh, to everybody. We are starting this webinar now. Thank you for joining us today. I know that we'll have more people joining as we go forward, but I want to start on time. My name is Neeraj Gupta. I'm the Technical Director for Subsurface and Carbon Management work at Battelle. And I think I know many, if not all of you. So it's good to see many familiar faces and also some new faces on this webinar. This webinar series is a continuation of the technical outreach that we have started under DOE-funded regional partnership programs like Midwest Regional Carbon Initiatives and MRCSP. And at Battelle, we would like to continue that technical outreach, both on CCS, but also all of the emerging energy topics, whether it's enhanced oil recovery, how to increase the use of coal, how to work on geothermal energy, how to work on nuclear energy. So this will be a broad set of series of webinars that we would start about on a monthly basis. And these will be shared through our mailing list that we started under the MRCI program, the Midwest Regional Carbon Initiative program, and also through LinkedIn. If you would like to be on the mailing list, or if you would like not to be on the mailing list, please do let us know in this case. This meeting will be recorded, and we will make a decision to share most likely through the MRCI website, the midwestccus.org, or the Explore ACS project website, explore-acs.org, with some editing, so we may not post a Q&A. I want to start with a welcome to everybody who has joined so far and others who will join. Just for housekeeping, there will be a brief Q&A period after each of these presentations, the two presentations. So please raise your hand if you have a question. You could also post it in the chat, but we may or may not get to it. And we will leave some time after both webinars for additional questions or discussion if somebody wants to stick around. But currently we have about 5 minutes for each Q&A session after each webinar. I want to start also with the safety movement. And there's a lot of safety topics, but what I want to say is that as we plan and our projects and field work, it's very often easy to overlook what you would need for safety. Having done a lot of field projects by our team, whether drilling, injection of CO2, please make sure that you budget enough time, appropriate staff, and support, as well as budget for safety oversight and safety planning on your projects, because I think that could make or break any of the projects we do for the industry. So with those general words, I do also want to thank the sponsors for both of these webinars, and both Joel and Jared will mention the sponsors. But broadly, I want to thank DOE, Department of Energy, so Hydrocarbon Office, for their sustained support for Battelle programs over last 2 or 3 decades. And what you're going to see today is the outcome from those projects. So our first speaker will be Joel Sminchak. My long-term colleague, Joel, has been working with us for more than 26 years on CO2 projects. So really one of the global leaders, technical leaders in carbon management. And Joel will talk about what we call the Explore ACS project, really looking at, is it feasible and what would it take to do CO2 storage and carbon management in Atlantic, the US. And of course, this has global relevance for carbon management in many areas where onshore storage potential is limited, but there is significant offshore potential. So Joel, please go ahead.
Thanks, Neeraj, and thanks everybody for showing up here. And I'm happy to give an overview of this project here. I think Neeraj did a good intro, so I'll get right into it. Won't dwell on this disclaimer, but it's required for all of our projects. Before I get started, I would like to echo Neeraj's acknowledgments and thank DOE and ETL for supporting this project and other projects. This project was mainly supported through this Explore ACS grant 32407, but it's also built on previous research through MRCI, MRCSP, Battelle, Rutgers has done a lot of pioneering work in this area, Maryland Geosurvey, Delaware Geosurvey, Lamont Doherty, too many others to mention, but just thanks to the everybody and definitely team effort. Explore ACS, Battelle was the lead, but we were also working with Aker Solutions, CarbonVert, Rutgers, TRC, TGS, Lamont Doherty, Amrise, Maryland Geosurvey, and EQT and Enbridge also provided technical advice on the project. So to get you situated, this map shows our kind of our study area. We're looking at this offshore, what they call this outer continental shelf, off the east coast, northeast coast of the U.S. So in this area, you have relatively shallow water, 50 to 300 feet deep, that extends 50 to 100 plus miles offshore. And, there's been some wells drilled back in the 1970s, early 80s, about 44 wells, these black dots, that kind of give us some glimpse into the subsurface that we were studying for carbon sequestration feasibility. Many of you have probably been to the, East Coast, some of these barrier islands, right? Like Jersey Coast and Ocean City, Maryland. So this is kind of what it looks like. It's a nice beach setting. And then, relatively shallow waters. So it's pretty accessible for drilling. There's a mixture of sand, mud, gravel out there. And then state waters extend about 3 nautical miles offshore. Beyond that, it's considered federal waters. So as far as the subsurface, there's these three large regional geologic structures, this Baltimore Canyon Trough, which is the focus of our research. There's this Long Island platform and this Georges Bank Basin. So if you drew a cross section through the earth through here from A to A prime in this area, you would have very thick sediments in this Baltimore Canyon Trough. So over, this is meters, so over 8,000, 10,000 meters, so that's 30,000 feet. And then sediments are shallower here at this Long Island platform and deeper in this Georges Bank Basin, but it's kind of remote. So we're focused on this Baltimore Canyon Trough, and to be specific, some of this Logan Canyon rock formation, this Mississauga rock formations. They're sort of at the right depths. They're deep enough, but not too deep for carbon storage. So as far as the data set available in this area, there are, again, these 44 wells shown as these kind of red dots here. So the wells are pretty far offshore, actually. So this is right here, the edge of the shelf, and this is considered continental slope where water gets very deep, upwards of 6,000 feet. So that would be deep water. So we're focused on the shelf here. There are rock cores collected from these wells, that they're rock core tests. So it's a pretty decent data set, but again, it's compared to like the Gulf Coast of the U.S., it's pretty sparse, and then concentrated in some areas. But there is additionally these seismic lines that are shown in these grids. So a lot of seismic out there that we can kind of supplement the well data with. As far as the goals of the project, we were again that there's a previous research has indicated that there's very large storage resource in this area. So it's been estimated at 150 to 1,100 gigatons. So that's enough for hundreds of years of CO2 storage. So it's a good resource. There's a lot of industry in this area. So this shows CO2 emissions, point sources. So in the Hudson River Valley, the Delaware River Industrial Corridor, a lot of industry. They have very few options for carbon sequestration onshore. So offshore resources would provide them with more options. And then there's opportunities, right? It's again shallow water, large area. We'll go over these favorable geologic properties. But yeah, there's also challenges, right? There's relatively limited exploration, lack of infrastructure. There's no oil and gas production in the offshore areas, obviously environmental stakeholder issues, and then challenges to source sink routing on shore. So the objective of this project was to come up with a plan, basically a preliminary design for CO2 storage to see what it would look like, look at options to minimize environmental impacts to local communities, make it more acceptable, look at, logistics, drilling well fields, and, preliminary costs for offshore storage in this area. So the project approach was three-pronged. It included looking at stakeholder feedback, looking at the CO2 storage resources, geologic setting, cap rock, well field design, what are the risks, and then coming up with the infrastructure necessary to construct these CO2 storage systems. So pipelines, injection wells, manifolds, what sort of exploration, what sort of safety do you need out there, and roll this into a CO2 storage development plan. Early on, what we realized was that, many options may be necessary for this area. There's you're not going to be able to have just like one massive CO2 storage project. You might need to have a mixture of low to high level of designs out there. So just to give you some context for background for those of you, or a little refresher on CO2 storage, you need several things. You need a reservoir, right, that has to be over about 2,600 feet deep and then not classified as a drinking water aquifer. It has to have capacity, it has to be thick and extensive. It has to have injectivity, so you have to be able to inject these large volumes. You need a confinement and a seal. Then you need containment, so you want to make sure there aren't any pathways where the CO2, because the CO2 will tend to migrate upwards. So you need a trap and you need to make sure there aren't pathways upward. So as far as one of the first things we did on the project was to look at, where are the areas where carbon sequestration are feasible in the offshore Atlantic, Northeast Atlantic. So project team developed these, what they call common risk segment maps. So they look at the subsurface features, the depth, the thickness, the properties of the reservoirs. They look at cost factors. So like how far are you from the shoreline? Are you in this really deep water? That'd be really expensive to access. And then operational freedom, we look at like environmental features, obstructions. There's shipping lanes. There's these, fiber optic cables that are showing these red squiggly lines that go offshore. So some of these things you need to avoid. So you kind of stack all those maps together and grade things out. And the green areas, so where, carbon storage would be most feasible. Yellow are, medium feasibility, and red are areas where it'd be unlikely to site a CO2 storage project. So you can see there's a big area out there, and to kind of explore this, we looked at different storage scenarios. We looked at one in this Great Stone Dome structure. We looked at this Indian River deep scenario, and then this Indian River shallow scenario. So I'll kind of go over those next. So the next question we asked was what rocks are best for carbon sequestration along the Northeast Atlantic. So our results, and this is some work from Rutgers, show that there are these Cretaceous age rocks. That's a geological term for 66 to 145 million year old rocks that are they're roughly 5,000 9,000 feet deep. And so if you go from the coastline to the outer continental shelf, you can see these rocks kind of slope to the east and get deeper, and you can see they also get thicker. So there are good rocks out there. But what we found was that on a local scale, the rocks are variable, their properties are variable, related to when they were deposited, when ocean levels were rising and falling. So that affects their potential for CO2 storage. To do a site-specific design, you would need to do some additional, strat test well drilling, seismic surveys. But we were working with the data that we had, so we developed these three geological models for these three sites. So this is Great Stone Dome site. This is where we selected because we had pretty well a lot of data from strat test wells out there. So this site reflected a deltaic depositional environment. And so the geologists look at, what types of rocks are down there, what sort of depositional facies are present, sort of lithologic facies are present, and then they use that to estimate the porosity and permeability distribution and calibrate it to where we do have well data. So what they found was that, that very thick gross reservoir thickness, 1,500 plus feet, 14% porosity and 53 millidarcy permeability. So those are technical terms that talk about the rocks. And you can see these properties are, pretty variable. So you're not looking at a, big, thick sandstone that's just, uniform and consistent throughout the area. It's much more variable than we realized. So that was an important finding. The next site we looked at was what we call this Indian River Shallow site. So this is a site on the Delaware coast where you could drill a well on the coast and then come laterally out and complete the well offshore. So your CO2 storage would be offshore. So this site was different. It reflected these fluvial or river depositional environments. So you have these stream channels and things like that. They're a little bit more separated. They're not as continuous. But overall, it still had, excellent thickness, right? 2,600 feet, very thick, 12% porosity, 40 millidarcy. But again, a little bit more variable in its subsurface distribution. And then the last site we looked at was this Indian River Deep scenario. So this is a scenario which is closer to the shoreline, so it's more accessible. You wouldn't need a long pipeline to access it, but you pretty much have no well control. So this is actually a more realistic scenario. People aren't going to site their projects this far offshore. They'll probably be focused on closer to shore. So this is more, speculative, I guess, scenario where we had to look at regional trends, and Rutgers took the lead on this, and they've done a lot of good work on looking at these trends, depositional trends. So you can see things change as you go offshore. So that's important to look at. This model, we didn't have enough data to really dynamically simulate it, but it kind of gives you a glimpse into the subsurface, some of these areas where you haven't drilled a well. So the next question we asked was, how much CO2 can be injected in these rock layers? So, for this Great Stone Dome scenario, again, we're here, off the Jersey Shore, where we have a lot of these test wells drilled. So we have pretty good information from these wells. So we have a better understanding of subsurface there. So the reservoir engineers set up these simulations and determine how many wells would be necessary to inject large volumes of CO2. What they found was, like, if you had 8 wells, you could inject 17 million tons per year, total of 500 million tons over 30 years. So that's a large volume. So this would be a very large system. We kind of, we're looking at a system that was, industrial scale, because it's going to cost a lot of money to do an offshore CO2 storage project in this area. So you'd have to inject a large volume to make it worth it. They found that, you could cluster these wells from the same well pad to minimize, impact to the seabed. And what they also found was, the injection rates varied quite a bit. So this is over that 30-year time period. You can see some of the wells were less than 1 million tons per year. Other wells were over 2 million tons per year. So a lot of variability in injection rates. So that's a reflection of the variable geology. You can also see that the wells, this is the bottom hole, they call it bottom hole pressure. So, you kind of reach the safety limit on your pressures. And so you have to reduce your injection rates at certain times to make sure you're keeping the system safe. But promising results, for a large scale system offshore. We also looked at this Indian River Shallow scenario where, again, we're on the coast of Delaware, where you could site the well onshore and drill laterally offshore and complete it offshore. So this was a single well scenario. And the engineers found that you could inject, upwards of 2.5 million tons per year. So that'd be 75 million tons over 30 years. So this was, again, promising results. You can see here, this is CO2 saturation with depth. You can see you have multiple layers that are accepting CO2. Also, you can see, like, the coastline here, and this is state water boundary. So you can see that, you drill this well onshore, complete it offshore, but you can keep all your CO2 offshore. So that makes pore space access a lot more straightforward since, it would not require landowner approval to get pore space. So so the next question we asked was, what are the key factors for geologic setting for carbon storage in this area? Again, the message I'd like to leave with you is that these reservoirs are, more variable than previously thought. But despite this, there's these thick, laterally continuous units with reservoir quality, porosity, permeability that can accommodate, industrial scale CO2 injection rates upwards of 17 million tons per year. There's limited data in many areas, so you would have to do additional stratigraphic test wells and seismic to kind of confirm um, your findings, but you have to realize that you could have variable injection rates. So the next question we asked, what would a CO2 storage system along the Northeast Atlantic offshore look like? So one of the first steps the team did was to look at where the sources in the area or the region. TRC did this work, and so they mapped out all the sources and found that there's 78 million tons per year of CO2 sources. There's existing gas pipelines that could be repurposed for CO2, or you could run CO2 pipelines around gas pipelines. So there are some areas where you could site some of these pipelines. There's offshore what we call offtake points where you could cross ashore. And for wind energy and other applications, they use horizontal drilling, so you go under the these beaches, so you're not digging a trench across the beach, so it would minimize impact to local communities and the environment. And then there are pathways or routes in the offshore where you can avoid sensitive environmental areas and other features to run these offshore pipelines. So what would a CO2 storage system look like as far as a pipeline? So TRC kind of came up with some initial estimates, and they said that, it'd probably be a 16-inch pipeline. This is for the 17 million ton per year injection system. So this pipeline, they have like a concrete coating around it, so it sinks. So they use this S-lay method to lay down the pipeline on the seabed. So this gives you an idea what it would look like. And this is the pathway for the pipeline. So there are routing options for running these pipelines offshore. And this is, what the barge would look like. So this is, there's a lot of barge traffic in this area, so it wouldn't be uncommon to see something like this out there. And the technology's out there for pipelines. So there's also technology out there for these subsea injection systems. So Aker/Ener did the injection field design. And what they came up with was that you could use these, smaller jackup rigs to drill the wells. And then a lot of the injection equipment necessary. So like these injection wellheads, manifolds, these interconnections would all be subsea. So it would limit any visual impact, which is a big issue on the East Coast. But this is all available technology that is used in other areas of the world. They came up with this, what they call clustered wells with a central manifold. So you would have like one well pad with a manifold, and you would have 4 wells off that. And then these wells would be, drilled down and horizontal away from each other. But this would limit the impact and actually save costs um, to use this sort of clustered well with central manifold approach. So key factors for CO2 storage system infrastructure, we came up with this design. It seems feasible. It'd probably take on the order of 5 to 10 years, permitting, exploration, construction, baseline monitoring. So that's similar to other offshore energy projects. There's feasible routes. And again, this design can minimize impact to the local communities and the environment. So as far as a roadmap to making CO2 storage happen in this area, we think the timeline 7 to 10 years with permitting, strat test well, seismic, baseline monitoring, field construction, injection operations, which is similar to other projects, offshore projects, energy projects like offshore wind. Most equipment is 18 to 24 month lead time, and it's available. Then there's advantages to early movers, right? Because you could get the best lease, you could shape policy, obtain right of ways. So as far as next steps, wrapping things up, we think there's options again, scalable options from like low cost options to moderate to high cost options. Again, going from an onshore to offshore injection well would be relatively affordable. And then, working up to a large scale system offshore would obviously cost more money. So with that, I'll just wrap it up and say that, we think that this project kind of gives you a realistic design for offshore CO2 storage along the Northeast Atlantic. Long term, these options are relevant. We think modest funding would be necessary to kind of continue development. There's advantages to early movers, and point you to this website, explorer-acs.org, or Joy there if you have any additional questions or want any more information.